Now, covariance was a subject that I was asked to cover. What is covariance? It's a question about how do reference frames affect physical laws? Does the motion of the observer, in other words, affect whether your physical laws are correct or not? Mathematically, we could say if I have an equation which involves the motion variables, and I ask if I change the coordinate system, like from Cartesian to polar, is the equation still the same form? Does a coordinate system change, like Cartesian to polar? If it doesn't change, then we have weak covariance because all you're doing is changing the mathematical structure. If you change the reference system, though, not the coordinate system, if you have an observer on Earth and one on a satellite, and you ask, what are the changes in laws from if I go from Earth to satellite? If those equations are the same form, then you have strong covariance. For example, if F equals ma is true on Earth, is it true on the satellite, where F prime equals ma prime are the measurements made on the satellite? So that's covariance. This is an important factor in physics because there are two types of reference frames. There's the Galilean frame, where anything that's moving at a speed v obeys this formula. According to Einstein, in order to keep the speed of light constant, you must use Lorentz transformations, which are shown in this red box. In this chart, we're going to compare Newton and Maxwell laws according to whether we have no ether, or we consider the mainstream, which is Einstein covariance. All right, if we ask, are Newton's laws covariant? Well, they obey Galilean's law, and the answer is yes. Maxwell's laws, though, the laws of electromagnetism, do not obey Galileo's law. They obey the Lorentz law if you require that the speed of light is constant. In other words, if special relativity is true. So when in the 1900s, when they knew that there was a conflict between mechanics and electromagnetism, they had a choice. Do I make Lorentz Galilean or do I make Galileo Lorentz? But what they chose, the mainstream choice was, we'll make Newton's laws obey Lorentz transformations. And what that means is the gamma factor, which is the square root in the denominator, which contains the v squared over c squared, that's going to be forced into the equations, even though it does not appear in the Galilean equations. So by forcing Lorentz to be used for both mechanics and electromagnetism, the consequence of that was that the v squared over c squared became part of what is experimentally measured because it's part of the equations, but it is not part of the equations when it's Galilean. All right, so the correct prediction of covariance will be making mechanics and electromagnetism both invariant under Galilean transformations. Okay, we're going to look at electromagnetic induction and look for any violations of relativity. I hope the guys have the video set up, and if so, we can look at the video before I continue with the slides.
Yep, pulling it up now. All right, you're good to go, sir.
Okay, I'm back with a small screen and myself in the lower left.
Yep.
Okay, let's see. I need the full screen.
There you go. I think it's at
Oh,
full screen.
okay. Thank you.
Good. No problem.
Okay. Okay, what we saw in the video was the actual experiment which tests Faraday's law. In this slide called Faraday's anomaly, we're going to see why some of the predictions of Faraday's law are not true. First of all, what is Faraday's law? The EMF, the voltage produced, which is the generator principle, depends on a charge, Q, moving through a magnetic field, B, with a speed, V, and what we must have is the speed of the conductor, C, relative to the magnet. So Faraday's law originally said you must measure the speed of the relative speed of the copper, the conductor, and the magnet, the iron. What you saw in the experiment was a copper disc, which is the conductor, located directly above an iron disc, which provides the magnetism. A motor provides the capability of spinning either one independently. And up here we have two brushes which pick off the voltage between the inside and outside of the conductor. And as you saw in the video, the wires connect to an oscilloscope, and you saw whether there was voltage produced or not. So I'm going to go through the results, the results of the test for those that are important. In this diagram, oh, come on. In this diagram, we see a chart of all the possibilities.
If you just kind of like click on the left of the slide, yep, it should go
Yeah.
away. There you go.
All right. The chart shows that there are 8 possibilities for rotating disc, that is the copper, rotating magnet, or the meter rotating. We are only going to consider the meter as stationary. So there's only going to be 4 possibilities. Number 2, line 3, 5, and 6. Those are the ones that we consider where the meter is stationary, the oscilloscope. And in this case, the disc rotates and the magnet is stationary. So Faraday's law would predict that there's relative motion between the two. And over here, we see the voltage is correct as predicted by Faraday's law. On line 3, the disc rotates and the magnet rotates. Now, according to relativity, the two are rotating together. There's no relative motion, so there should be no voltage. But in this column, we see in red, there is a voltage. So line 3 violates Faraday's law if you use relativity. The other ones that we want to check are meter stationary, so that's line 5. The disc is stationary and the magnet is stationary, and that's no relative motion, and there is no voltage. That's correct. Disc stationary and magnet rotating, that should produce a voltage, but it doesn't. So this is the second violation of Faraday's law using the law of relativity. What I want to look at next is the summary. When the disk spins, we found that the test agreed with Faraday's law, and so did special relativity. Now, if I use, instead of the relative motion between the conductor and the magnet, I use the motion of the conductor relative to the Earth, the lab frame, that also agrees. When I considered the magnet was spinning and the disk wasn't, then I get no for special relativity, and that doesn't agree with what the experiment shows, which when they both spin, there should be no EMF produced. So there are two conditions in which Faraday's law are violated. But if I use, instead of conductor relative to magnet, I use the conductor relative to the laboratory, I do correctly predict the voltage, the generator principle. So SR in electromagnetism is rejected, and the alpha model, meaning one in which there is an absolute lab frame corresponding to, which predicts correctly the results that we get. So we see in mechanics and we see in electromagnetism that the lab frame must be used in order to predict correctly using the laws of physics. Now, there's something that was just discovered recently called the vector potential. I identify it with the ether, which is why I call it the ether vector potential. A quick review of what vectors are. A vector is something with size and direction. We indicate it with a bold letter. The vector could be representing a line in space, or it could be representing something rotating. The way we tell what's happening, we use the inverted delta operator. We use the nabla. The nabla applied to a vector indicates whether the vector is changing in shape or in space. So this is called a gradient. The nabla plus a dot applied to a vector is called a divergence. That tells you if there is any radial change in the vector. In other words, is it getting bigger or smaller? The notation with the nabla and an X is called a curl. The curl tells you whether there is a change in the rotation of the vector. So this is a way of conveniently telling us, using mathematics, whether a vector is getting bigger or smaller, or whether it's rotating, or whether it's constant, then it would be 0. So the curl finds everything that is rotating. If we apply the divergence, as we do here, then the divergence finds everything that is radially changing. Well, the first one eliminates all expansion, the curl, and the divergence only picks up what's radial. So the two together must calculate 0 for the amount of change. So this is an identity that's always true. For example, in Faraday's law, if you wanted to interpret this, you would say the curl of E indicates that the electric field has what? A rotation. So if the curl of E is not 0, then there must be a change in rotation. And this must equal the time rate of change of the magnetic field B. So this is how you can look at Maxwell's laws and interpret what they actually mean. We know the divergence of B is equal to 0, which means magnetic field lines never end. They always consist of circles or loops. suppose we let the vector B be the curl of some vector A. Now, mainstream picked A as the symbol, but it's interesting because ether is what it really represents. If B is the curl of A, then the divergence of the curl of A must be 0 because of this identity. If we use the other Maxwell's laws, we find the electric field is the gradient of a scalar potential phi minus the rate of change of A with time. Now, if you use the electric and magnetic fields, there are 6 of them, 3 in space for each one. But if you use the vector potential A, you have only 4. Maxwell's laws, which are expressed as electric and magnetic fields, simplify to only 4 things that are needed if you use an ether field, an ether vector potential. And this is more fundamental than E and B because from the vector potential, I can determine what the values of E and B are. Now, there's an experiment in that recently was done, which connects electromagnetism with quantum mechanics. It's called a Aharonov-Bohm test. If you have a solenoid, an electromagnet, it produces a strong magnetic field inside and almost 0 outside. If we ask what happens to electrons when they go around the cylinder, then that's predicted by Schrödinger's equation. So this is quantum mechanics being applied to a classical electromagnetic case. Electrons are being sent around a electromagnet, a solenoid, and we can ask, what are the predictions that quantum mechanics makes? The diagram down here shows that if we set an electron beam, 2 of them, through a barrier around the magnetic field of the solenoid, then the magnetic field, according to theory, it's non-existent outside the solenoid, so there should be no effect. But quantum mechanics shows that there's an interference pattern if I combine the electron beam from the original source. What this means is that a classical electromagnetic theory would predict that there is no effect on the electrons, but quantum mechanics says, yes, there is, because we see an interference pattern. So this proves that the A potential, the A vector potential, must be used in order to predict correctly what happens in this case, which is predicted and confirmed by quantum mechanics.